Hello, everyone. Welcome to my talk. My name is Timur Doumler. I'm Timur Audio on Twitter. I am developer advocate at JetBrains, and normally JetBrains always has a booth here at ACCU. Unfortunately, due to current events, the rest of my team cannot be here today, as Felix also mentioned in his introduction. However, I'm here, so even though we don't have a booth. So if you are interested in talking about C-Line, the C-Line IDE, or any of our other products, or if you have any feedback or comments or complaints or anything like that, then I do want to talk to you. So please come and find me. I'll be around all week here. And the other thing I wanted to say is that, kind of a disclaimer for this talk, is that I was originally hoping to present this as, kind of a completed project. This is what I've done. Like, this is the code. This is the GitHub link, But unfortunately, again, due to current events, due to multiple clusters of current events that have been going on, I unfortunately didn't have quite as much time to devote to this project as I was hoping for. So therefore, it's all kind of still very much in a work in progress kind of state, and this is why it has version 0.1 here below the title. So please bear with me, and I will give another iteration of this talk at C++ Now in a month, and also probably at other places afterwards. So I'm going to keep iterating on it and adding more stuff as it progresses. So if you do have any feedback or ideas or stuff like that, then please, again, talk to me. So we are talking today about a lock-free atomic shared pointer. And I'm very happy to see that so many people have turned out for this rather niche subject. So thank you very much for coming, very much appreciated. So there are like three things here that we need to talk about. There's like lock-free, atomic, and shared pointer, right? And we're going to talk about all three of them kind of one after the other. And let's start with shared pointer. So who here knows what a shared pointer is? Okay, that's good. Who doesn't know what a shared pointer is? Okay, also good, because I have a minimally short introduction. This is what the C++ standard says about what a shared pointer is. It's basically a pointer, usually to an object on the heap, which implements semantics of shared ownership. And typically it also implements reference counting in such a way that it does reference counting, and the last owner that ends up with this object is responsible for destroying it. So that's a very useful, very widespread utility in C++. Shared ownership pointer. Here's basically the gist of how it works under the hood. This is basically the bare minimum that you need to know about the implementation. Basically, there's a shared pointer itself, and it has a pointer to a control block. And the control block is this thing on the right, has a pointer to the actual object that's being managed. Then it has an atomic ref count. And then it has the object itself, which may or may not be within the control block. It might be allocated separately or inside the control block, depending on whether you created it with make shared or not. So here in this case, we have one shared pointer, which is pointing to that control block and managing that object, so the ref count is 1. If you copy that shared pointer, you get another shared pointer, the ref count increases to 2, and now we have 2 shared pointer instances pointing to the same control block and managing the same object. If one of these gets destroyed, the ref count goes back to 1. If then the other one gets destroyed, the ref count goes to 0, and at that point, the object is going to be deallocated, and then eventually the control block itself will also be deallocated. So that's basically how a shared pointer works under the hood. Let's talk about the atomic bit. So what does atomic actually mean? And atomic and lock-free, I need to stress this, are two different things. And we're going to see this later as well. So atomic, the Greek word atomos, means indivisible, which means an atomic operation is something where there is really only just a state before and a state after, but you cannot observe, for example, from another thread, any kind of in-between state. So that also means that an atomic operation is free of data races, which is very important. And that means it's thread safe. Of those of you who do know how a shared pointer works, can you tell me if a shared pointer is thread safe? Who thinks that a shared pointer is thread safe? Okay, a few people. Who thinks it's not thread safe? Okay, who thinks that neither of the two options are correct? Okay, yeah, people, you know what you're going to talk about. So the standard doesn't actually say very much about whether or not shared pointer is thread safe. The only thing the standard says is that changes in use count, which is the ref count, do not reflect modifications that can introduce data races, basically. So whenever you do something that just modifies the ref count, that's not going to introduce a data race. That's basically what this means. So in other words, if you have a shared pointer, again, with ref count 1, and then you copy it, that modifies the control block, right? That increases the ref count. If you would simultaneously do this copy also on another thread, that's not a data race, because the ref count increment is happening atomically, so both threads would agree on who incremented what, when, and what the ref count is afterwards, so everything's fine. So what you can do is you can take a copy of a shared pointer on one thread and take another copy on another thread simultaneously, and even though they modify the same control block ref count, it's fine. You can do those simultaneously. That's not a data race. And then once you have these two different instances of shared pointer, pointer 1 and pointer 2, each one of those on those threads, you can modify pointer 1 on thread 1, you can modify pointer 2 on thread 2, and you can do with them whatever you like simultaneously, even though they point to the same control block initially. And that's not going to be a data race, if every thread has their own instance of shared pointer. It gets more interesting if you flip the second one around, and now we are copying or reading the shared pointer on one thread and then assigning to the same shared pointer instance on another thread. Who thinks that this is okay? Okay, you people really know already what's going on, so I can speed up. This is good. Who thinks this is not okay? Okay, so yes, you're right. This is undefined behavior. This is a data race. And when I first heard about this, I found it really difficult to reason about but what, when is it a race, when is it not a race? But then it's actually really easy, because it's the same it is with an int, right? If you read an int from one thread and you read the same int from another thread, that's fine. But if you read an int from one thread and write into that int from the other thread, that's not fine. So if you look at it from just pure kind of modifying a value kind of perspective and ignore what's going on under the hood, it's actually pretty straightforward. So yes, this is a data race. You cannot do this with a stitch shared pointer. However, this comes up in real code, and however, there is a solution to this, right? This is a solved problem. So you obviously can solve this yourself. You can wrap the shared pointer. You can add a mutex that protects it and wrap the whole thing into some kind of wrapper and do it by hand. But also we have utilities in the standard library that can do this for you. So in particular, ever since C++11, which introduced shared pointer, we also have these, which are these freestanding functions, which do atomic operations on shared pointer. And we had these for as long in the standard for as long as we had shared pointer itself, right? So they have always been there since C++11. And they look a bit weird. There are these freestanding functions, std, : atomic, underscore, whatever you want to do, the operation. And then they all take as the first argument a pointer to the shared pointer that you want to read, write, modify, whatever. So they have this bit odd interface. But they do what they say on the tin, right? So with those freestanding functions, you can solve the race that you saw before like that, right? So instead of just reading and writing the naked shared pointer, you do an atomic load using the free function in one thread, and you can do an atomic store in the other thread, and that's fine, right? By the way, if you do have any questions, just wave or something, and we can talk about them as long as we go. So this is okay, this is valid. It's actually deprecated in C++20 because we have something better. And this is what I want to talk about next. So actually these free functions, they do the job, but they're not great for at least two reasons. First of all, the first reason is safety. You have to remember to use them, right? If you just write the plain shared pointer thing and you read and write from different threads, nothing's preventing you from writing that. And by default, you have a race. And you have to remember to instead use these free, quite verbose, freestanding functions on every access to the shared pointer, everywhere where you could have a data race. So you have to remember actively to use them, right? So they're not there by default. So it's kind of unsafe. And the other problem is that you can't really efficiently implement them because they're freestanding functions, right? Ideally, if you want to solve this with a mutex, you want to have the mutex right next to the shared pointer that it's supposed to guard, right? This is how you would do it. But if you have a freestanding function that takes a pointer to a shared pointer, it needs to work with any shared pointer. So it basically needs to either have some kind of lookup table where you store like a mutex, you like have a map between like every shared, like a shared pointer and like a mutex that guards it somewhere else, which is going to be overhead. Or even worse, and this is what some implementations actually do, you have just a global mutex for all shared pointers, which is really not a very good solution, but this is what at least some standard library implementations do, as far as I know. So that's not really great. So to solve that problem, Herb Sutter proposed all the way back in 2014 that we should make this a class. We should actually have an atomic shared pointer in the standard. And he actually proposed atomic unique pointer, shared pointer, and weak pointer. In the end, we didn't get unique pointer, but we did get shared and weak pointer in the standard. So as of C++20, the arrow in the standard, stood atomic, stood shared pointer, and the kind of freestanding functions that you saw before, they're deprecated. You're not supposed to use them anymore because this is better, right? It's safer, and it can be implemented more efficiently as well. Actually, funny side story. So Herb initially proposed it like this, as a specialization of stood atomic with the angry brackets. And then the committee said, well, we don't really want this to be a specialization of stood atomic because stood atomic is only supposed to work with trivially copyable types, and shared pointer isn't trivially copyable, so it's really something else. You should call it stood atomic underscore shared pointer. And then Herb did a revision of the paper, said, okay, now I'm proposing it as stood atomic underscore shared pointer. And then the committee changed its mind again and said, oh no, actually we do want to have it as a specialization of stood atomic. So this is what we got in C++20. It is a specialization of stood atomic, although it's kind of a special one. And so with that, in C++20, you can now write it like this. Right? If you want to, so you, instead of using a shared pointer, you use an atomic shared pointer. And now, as soon as you have this atomic shared pointer, you can do just loads and stores into it, and that's going to be atomic, and that's going to be thread safe. And you don't even have to write these loads and stores explicitly, although I like to do that in my code because it makes it explicit. Hey, there's like an atomic operation going on here, but you can just omit them and like write kind of the naive code, such as assignment, that we had before, but because it's an atomic shared pointer now, this is also safe, and it's actually doing exactly the same thing as this. So these are equivalent. They're going to result in the same code being generated. So this is great, right? Except there is a small problem. They are not lock-free, like the implementations that we have in the standard library today. So let's talk about lock-free, what that means. Like, why do we want lock-free? And lock-free is actually not the same as atomic. What lock-free means is literally that. There are no locks, right? There are no mutexes. And so instead, the thread synchronization is implemented via atomic operations that are supported directly by the CPU, right? And so that depends on like what variable you have in the atomic and whether your CPU architecture supports atomic operations for that data type, right? And that is actually very suitable for low latency and real-time applications, which are things like audio processing, which is my background, or games, or high-frequency trading, or lots of embedded applications like cars, elevators, moving a robot arm, stuff like this, where like basically you have a task which is on a tight deadline, right? Oops, I think we lost the slides. Oh, no, they're back. Okay, good. So whenever you're on a tight deadline, you have to complete, the correctness of your code depends on how fast it is, right? You don't want to be waiting on a mutex, because if you're waiting on a mutex, you have no idea when the mutex is going to be released. You can't really reason about fulfilling your time deadline. You can't reason about how long that might take. And there's actually a second problem with this. Not only do you not know how long you're going to wait for a mutex and whether or not you're going to make progress at some point, the second problem with mutexes is that they don't care about thread priorities. So if you have things like audio processing or things like high-frequency trading, finance stuff, you typically have, for example, like one high-priority thread, which is doing like the hot path, right? Like the operation that really needs to happen really quickly. And then you have like other kind of tasks that are less important that are somehow synchronizing with it and like sliding data in and out as you need. But then if that high priority thread waits on a mutex, the mutex doesn't care about thread priority. So you might end up waiting on a mutex that is being held by a low priority thread. And then you get this thing called priority inversion, and that basically wrecks your whole like idea of like making it kind of low latency and high priority. But with lock-free algorithms, you don't have that problem, right? Because you don't have the priority inversion because you're not ever waiting on a mutex. And you have this guarantee that your program is going to make progress. So one example where you kind of need this lock-free approach is actually something that I was talking about in my very first conference talk ever, which was at CVPCon 2015, which is called C++ in the audio industry. Back then, I was actually still working in the audio industry. I was working at Juice. You can see I'm wearing a Juice shirt there. It's like, hi, Tom. And the use case here is that you have an audio plugin like a synthesizer, and you have one thread, which is the main thread with the GUI, and the user can edit something in there. It's like an envelope, something that basically changes the sound as you drag it with the mouse, like it changes how it sounds. That's really cool. And then the other thread is your high priority thread, which is producing the audio, and then that just is on this like real-time callback. And that thread just needs to continuously produce audio. It can't wait on a mutex because then it will stop producing audio. You will get a glitch. You can't, potentially, right, if you're waiting for too long. So you can't do that. So you have to somehow share this object between the threads and kind of manage the lifetime of the object between the threads without introducing locks. And so if you don't have a lock-free atomic shared pointer, then what you end up doing is you end up having an atomic raw pointer, which is going to be lock-free. And then you have to manage the lifetime of the object manually. And this is basically, there's pretty much no way you can get this right, or at least me, because it's just too complex and too messy. So that's not really good. So we need something better here. And this is actually where I committed a mistake in the talk. Like, it's one of my two major blunders that I committed at past conference talks. This is the first one. And so at that talk in 2015, I said, well, you shouldn't be managing the lifetime manually because you're probably going to mess this up. So what you should do is you should use a shared pointer, and in order to make it thread safe, you should use these atomic load and atomic store freestanding functions. Because back then, 2015, we didn't have the atomic shared pointer specialization yet. We only had the freestanding functions. So I just said, use them and everything's going to be fine. And I completely overlooked the fact that they're not lock-free, and they're going to introduce mutexes in your code. And if you have a synthesizer which is waiting on a mutex instead of producing sound, then your users are probably not going to want to use that synthesizer, so you should not do that. So this was a mistake, which I hereby correct. Don't do that. Turns out there's actually another thing about this, which is for this specific problem where you kind of like modify an object on like a GUI thread and then kind of publish it to the real-time thread. You also have this problem, which I kind of talked about a little bit, that you also want to make sure that the real-time thread is not going to be the thread that ends up having to destroy the object, because that's also not lock-free, because that's a deallocation. And so there's actually a completely different pattern, which is a much better solution for this particular problem, which is called RCU, read copy update, which I wasn't aware of at the time. And it's a more elegant solution for this particular problem. So that's going to be a different talk about RCU, not today. Today we're going to talk about atomic shared pointer, and there's actually another case where it is really, really useful, which is lock-free structures. And in particular, lock-free structures in C++, which notoriously suffer from the ABA problem, which is basically you have multiple threads, and one thread changes a value and then changes it back to what it was before, and the other thread didn't realize that anything changed, and then the state of your whole system is completely messed up, and like you're not going to have a good time. And solving that problem with lock-free structures in C++ is notoriously not hard. And here we come to the second big blunder that I committed at past conferences, which was actually here in this very room 5 years ago, where I did a talk called Lock-Free Programming with Modern C++. Of course, I'm going to give a talk about that. What could possibly go wrong? And I was actually talking about how to implement like a lock-free queue with like multiple readers. And I was like, okay, so you do this, 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 and that, and here's the code, and it works, and it's great, right? And I had that on the screen. And it had a bug, which I didn't see. It didn't solve the ABA problem. And then Frank, who I don't think is here today, but was in the room 5 years ago, actually pointed out to me, yeah, I don't think this is quite right. And so he actually came up on the stage, and like we had a little conversation about, yeah, like, nah, I don't think this is quite right. And I was like, what do you mean? This looks right to me. But then, unfortunately, there was a little accident. Frank actually fell off the stage. And so we ended up not finishing that conversation. And I was still thought that it's probably fine. But then, of course, somebody else pointed it out on the YouTube comments afterwards. Hey, your lock-free queue actually suffers from the ABA problem. It's not correct. And it's also not very easy to fix. Like, it's actually really, really hard to fix. And it's not something that I could have just patched up or something like this. Because it kind of invalidates the whole algorithm, basically, if you didn't account for that problem. And if you look at lock-free queue, like multi-reader, multi-writer lock-free queue implementations that are used in production, so are known to be correct, like, for example, the Moody Camel lock-free queue or the Boost lock-free queue, and you look at what's going on there, you see it's really, really, really complex. They have like multiple like cast loops, and it's like quite long, like all the like push and pop operations. Like it's really, really complex. It's very, very, very hard to get right. And the main reasons for that, like the two main sources of complexity here is, A, you have to manage the lifetime of the kind of elements across the different threads that might be pushing or popping, which is a very difficult problem. And then there's the ABA problem, which you need to account for, right? And so those two things together make these algorithms like really, really hard. But it turns out that actually atomic shared pointer kind of encapsulates both of those problems really nicely, because it does deal with exactly that, like lifetime management. And it does not suffer from the ABA problem, because it doesn't deal with indices or something like this. It actually knows like the identity of the object that it points to. So it doesn't have the ABA problem. So it kind of very nicely encapsulates all this complexity that you normally have in these lock-free structures. And it turns out that if you use lock-free atomic shared pointer as a building block for these lock-free structures, and you like build them on top of that, they become a lot easier. So here is an implementation of a lock-free stack by Herb Sutter, which is one of his motivating examples in that atomic shared pointer proposal that we saw. And that can do a pop front and a push front, and also a find of an element in the stack. And you can do all three of those things simultaneously from as many threads as you like. And it just works, and the whole implementation fits on a slide. That's it. This is the whole thing. So this is really, really kind of compact. It's really elegant. And it's not very complex, because all the complexity is kind of hidden in the atomic shared pointer here. And if that atomic shared pointer is lock-free, then the whole thing is lock-free. So this is an example for a stack, but you can also find an implementation of a queue, like a lock-free queue, which is also built on top of atomic shared pointer, which is similarly kind of small and elegant. And there's also other lock-free structures. So you can use atomic shared pointer as a building block. It's not necessarily going to be the absolute most performant implementation that there can be, but it's going to be probably good enough for a lot of cases, and it's going to be very elegant and very concise, right? And so actually there was this other talk also 5 years ago by Fyodor Pikus, who was talking mostly about ACCU, but also was saying, he basically identified these like 3 different kind of like building blocks that you can use as alternatives in order to like build lock-free structures on top of them. So he said there's ACCU, then there's hazard pointers, and then there's the atomic lock-free shared pointer. And so they have like slightly different trade-offs, as you can see in the table. But you can use all 3, like either of the 3, as a building block to like build lock-free structures on top of. And so he was talking about this as if like, yeah, of course, lock-free atomic shared pointer, it's like Everybody has one of those. I have like one of those lying around. Everybody knows how, like, where they are and where to find them, and of course it's great. That was me in 2019. I was like, well, we're going to get one of these in the standard, so surely it's going to be lock-free, right? Right? Because that's awesome. That gives us like all these. That's such a useful tool. It's so cool. We can use it for all these things, right? Lock-free programming is going to become so much easier. Well, and now it's time for a quote from my favorite Arnold Schwarzenegger movie, which is Commando from 1985. Wrong. Yeah, so it turned out, so I actually went on Twitter because I genuinely didn't know back then. This was 2019. It was like I was on the committee, so I knew that we would get it in the standard, but there were no implementations yet. So I said, hey, dear library implementers, like, we now voted this into the standard, so surely you're going to be implementing this over the next year or two. So surely you're going to like make it lock-free, right? Because that's what everybody wants, right? Because it's awesome, right? And then STL, like the maintainer of the Microsoft standard library, actually replied to me and said, well, I don't know if this is even implementable. Like, you would have to atomically modify like the pointer and the ref count simultaneously. Like, how could you, I don't think you can do this. And then fast forward to 2022, well, they did ship atomic chat pointer, which was not lock-free, Microsoft, and then GCC and GC12, which is not official release yet, but like the next release is also going to ship an implementation of atomic chat pointer, which is also not lock-free. And then Clang, the third big implementation, libc++. I don't know if they have an implementation, or if they're working on an implementation. I don't know. Maybe somebody else does, but I'm pretty sure it's also not going to be lock-free. Like, all the implementers basically said, nah, no. And so I was really confused because on the one hand, I had like Fjodor who was saying, yeah, of course, it's like one of the basic building blocks for lock-free programming. Like, of course, I have one of these lying around. It's like, cool. And then on the other hand, I had, like, somebody I really respect. And on the other hand, I had like the standard library implementers, which are very smart people who I also very much respect. And they were saying, I don't know if this is implementable. And like, yeah, no, we can't do this. I was like, how, like, there's a bit of cognitive dissonance going on there, right? So I was like, but what's the answer here? Like, is it implementable? Is it not like, does this guy have an implementation? But then why it didn't make much sense. So I started digging, and I found a blog post by Anthony Williams, which I think is, actually Anthony Williams is also here at the conference, although I do not see him in the room. He's online. Hi, Anthony. If you're listening to this, thank you for your work. So I stumbled upon Anthony's blog post, and Anthony was saying, well, I have an implementation. It's like closed source, it's in the just thread library, but I have it. Yes, so atomic, if you do it lock-free, you have to do a bit more work, it's a bit more complex, blah, blah, blah. Like, if it's like, in an uncontested use case where you only have one thread, like, it's going to have to do more work than just acquiring a mutex, which is like really cheap. So, but like in the case where you have high contention, lots of threads, it's going to be a lot better because it's lock-free, right? So it's awesome, and I have an implementation. So I was like, okay, now there are like two people talking about implementations. Still, the standard libraries don't ship one. How, and that one, like, at the time was like not accessible to me. But then I kept digging and kept digging, and it turns out there's actually 3 free open source implementations of atomic lock-free chat pointer that you can look at today. There's one version of Anthony Williams' implementation, so he has a version in his just thread library, which is closed source, which I have never seen. But he also has one on GitHub, which is kind of a proof of concept version of just lock-free, his atomic lock-free chat pointer algorithm. Then there is an implementation in Folly, which is Facebook's general C++ utility library, which is actually used in production, written by Dave Watson, who doesn't work at Facebook anymore, but currently being maintained by David Goldblatt, which is also on GitHub. And then there is this guy, Vladislav Tilbashev, who basically said, well, I don't really like Anthony's implementation, and I don't understand Folly's implementation, so I'm just going to write my own. And that's on GitHub as well. So I have talked to all three of those people. I have sent many emails to Anthony, David, and Vladislav, saying, hey, I don't really understand how this works. Like, why did you do this here, and why did you do this there? And all three of them replied, and I learned a lot from their emails, so thank you very much. It was definitely like the key thing in like figuring this out was like talking to these three people who actually had these implementations out there. So it's actually really cool to see that if you reach out to people who have done something cool, they actually answer and they write you back and they help you figure things out. So that's really amazing. It's like one of those reasons why it's such a great thing to be part of the C++ community. And I should also mention that Vladislav also has a blog post about this, which is called half a year of my life implementing atomic lock-free shared pointer, which I very highly recommend you read. Unfortunately, it's in Russian, so I can read this because Russian is my mother tongue, but you might not speak Russian, so maybe Google Translate can help you out. I hope it can, because it's definitely worth checking this out. Like, it's a pretty cool blog post. Right, so there are implementations, right? So not in the standard library, but other people have done it. So how would this work? Let's maybe talk about how you would go about actually implementing this, because clearly there is something worth spending time on rather than just saying, it's unimplementable, we can't do this, goodbye. And so let's look again at shared pointer. So we said, yes, shared pointer has basically a pointer to a control block. By the way, again, if anything's confusing or you have questions or you think something's wrong, please just wave your hand and interrupt me. Is anybody like with me? Am I talking too quickly? Is it? Yeah, it's good? Okay, cool. Feel free to interrupt if you're lost or anything. Okay, so we have the shared pointer, which basically is, it has a pointer to the control block, and the control block has the pointer to the actual object, and then the ref count. And so what do we need to do if you want to atomically modify a shared pointer in a lock-free way with like atomic CPU instructions? So what we would need to do, so you would need to update, like for example, if you modify it, right? You need to update the control block pointer, and you need to modify the ref count at the same time, atomically, right? And they're at completely different memory locations, right? Because we have the shared pointer here, and we have like the control block somewhere else on the heap, and we might have multiple shared pointers pointing to that control block, right? So the problem is, how do we modify two separate like pointers, or like one pointer and one index and separate locations in memory atomically at the same time without introducing a mutex? So that is called in kind of theory is called a double compare and swap operation. And it actually turns out there is a CPU that can do that. It's the good old Motorola 68000. And it has an instruction called cas2, which does exactly that. It atomically compares and swaps two separate memory locations at the same time. So for this particular processor, implementing a lock-free atomic shared pointer is going to be really easy and straightforward, which is kind of cool. Unfortunately, no modern CPU implements double compare and swap. That's not a thing these days. So how do we solve this problem then? Well, modern CPUs don't have a double compare and swap, but they have something else which is called a double width compare and swap, which is something different. Yeah, you should keep them apart. So a double width compare and swap basically means that you can atomically modify two pointers at the same time, or like one pointer and an index at the same time, given that they are adjacent in memory and also on the same cache line typically. So like next to each other, right? Which is not the case here. So how do we get from a problem that we can't solve, how do we reduce this problem to a problem that we can solve with double width compare and swap, where like the control block pointer and the ref count need to be next to each other. And it turns out there is an algorithm to do this, and it's really, really cool. It's called and basically all the 3 implementations that I'm aware of, the open source ones, they all use basically the same basic idea. And it's called split ref count. That's how some people call this algorithm. And as David Goldblatt said, this is a quote from him, the guy at Facebook, he said, it's sort of a folk algorithm, so you don't typically find this explained anywhere. So it's kind of like this arcane knowledge. But I did find 2 references to split ref count, which is one is like a blog post about differential reference counting, and the other one is actually Anthony Williams's concurrency book, which is, by the way, really, really awesome, and it does have a chapter about split ref count as well. And both of them talk about kind of reference counting and how you do that, how you make that lock-free. Neither of them talk about specifically implementing a lock-free shared pointer. So the context is slightly differently. So it doesn't directly apply to what we're trying to do here, but it is kind of the same idea. And the idea is like this. If we apply this to our problem here, which again, those 2 are sources don't directly talk about exactly this case, but that's what the implementations do. So instead of having 1 ref count, which is in the control block, you now have 2 ref counts. You have a local ref count, which is in the shared pointer itself. So it's next to the control block pointer, right? So we can atomically compare, swap, or modify both of them at the same time. And then we have a global ref count, which is just the ref count in the control block that we already had before. So we now have ref counts in 2 different places, right? And the whole algorithm revolves around how do we sync them, right? So that's kind of then kind of the interesting bit. So what you end up with is kind of something like this, where you have your atomic shared pointer, and then in there you have a structure, let's call it counted pointer. And this is pretty much what kind of how you can do this is you have a struct which contains the control block pointer and contains the local ref count, and then you put that whole struct into an atomic variable. So it's 2 words wide, right? So you can atomically modify it lock-free with double with compare and swap. And then once you have that, basically a modification of the shared pointer basically follows this general pattern where like load, store, and a compare exchange, like these are like the different methods you need to implement. They're all going to be somewhat different, but like the basic idea is basically normally you would modify the control block and then increment the ref count, right? This is the basic thing you would normally do. Here, what you do is you modify the control block pointer and increment like if you have to, and you increment the local ref count, right? And you can do this atomically. You can increment the local ref count and make sure that the control block is still the same as before. So you can do that with double with compare and swap. So you increment the local ref count, and then you increment the global ref count, and then you decrement the local ref count. So you kind of do the ref count increment locally, and then you kind of publish it to the global one, and then you decrement the local one. So it's like these 3 steps. But then what can happen is that another thread can come in and just like write another value into the shared pointer, and then your control block is going to be different. Like your local ref count is going to be different. So what you do is you increase the local ref count, and then you try in a loop, right? You try to increase the global ref count and decrease the local ref count again, so that the change is going to be in the global ref count where you want it. But if at any point in between another thread came in and modified the thing, then you just roll everything back and start over, right? And do that in a loop until you succeed. So this is the basic idea. And so let's look at how this would look in code. And I'm only going to show here the load function because this is kind of the easiest one, I think. And this is pretty much how it looks both in Anthony's implementation and in Vladislav's implementation. So the actual code looks different, but like the algorithm is pretty much the same, apart from like minor differences. So we have our atomic. So are you with me so far? Okay. So we have this atomic C-patter here. That's like the atomic counted pointer. That's like our double width atomic variable, which contains the control block pointer and the local ref count. So let's implement load. So the first thing we need to do is we need to increment the local ref count. And we need to do this actually in a cast loop here, because you want to increment the local ref count, but make sure that no other thread modified the control block pointer at the same time. And there's no 128-bit increment instruction in C++, so you have to do it with a cast loop. You have to say, okay, give me the current state. So these two, the counted pointer describes the current state of the atomic shared pointer, right? So store the current state and then increment the ref count and make sure that no other thread has changed the state. And basically that publishes the local ref count increment. And if some other thread changed the local state, you just try again. So once this compare exchange weak here succeeds, we have incremented local ref count. Now, basically, we're done with the local state. So now we can say, okay, this is the valid local state. Now we're going to make a copy of that, and we're going to later return this as our new shared pointer copy, right? So what we're doing with the load is we're returning a copy of the shared pointer that it holds, right? So this is the value that we're going to later return. So this is the second step. The third step, we increment the global. Yes. 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 Yes, thank you. Value should be CPTR, I think. Yeah. I think I named it value and then I named it CPTR. I didn't rename it properly. Sorry, I will fix this slide. Thank you very much. So yeah, value should be atomic CPTR. Then we increment the global ref count. That's just one atomic integer, right? So we can just use fetch add. And now we have to decrement the local ref count again. And the way we do this is we basically, say with a cast loop, right? We say, let's decrement the ref count and let's publish that change and make sure that no other thread overwrote what we just did. And if it did, then the compare exchange weak will fail, and then we have to try again. Yes?
How often in practice does this thread spin?
How often in practice does it need to spin? It completely depends on the contention, like how many threads. If you have no threads, no other threads, it's just this one thread, then on Intel, it will always succeed on the first try. On ARM, you have a slightly different implementation of hardware of the compare and swap, which can spuriously fail. So then it might very rarely fail once and then you have to do it again. But most of the time, it will go through in one go. But as soon as you have more threads hammering the same atomic, the probability is going to increase that another thread is going to be faster than you, and then you need to start over. We're going to see this later. And then there's this last thing here, which is actually a difference. So this is handled differently in Anthony's implementation and in Vladislav's implementation, where there's this edge case where if you incremented the global ref count, but then turned out somebody else has already done it for you, or somebody else, this is not the control block you wanted, basically, then you need to basically roll that back as well. And once this loop has succeeded, you're done, and then you presumably have some way of wrapping the control block that you got with a shared pointer and return that, and that's going to be your return value. That's done. So this is how the load works. It's quite complex. I'm not going to show exchange and store because they're even more complex. But basically this is hopefully this convinces you that this stuff is complex, but it is implementable. Okay, there is an algorithm that implements this stuff. It is possible to do this, and people have done it. So we should also observe that each of these atomic shared pointer accesses is going to have at least 3 atomic operations in it. And if the cast loop fails, it's going to be more, right, depending on how often the loop goes around, which is going to depend on how many threads you have. So that will definitely be slower than just acquiring a mutex, because just acquiring a mutex, if you're not waiting for anybody else, is very fast. So on average, it's going to be slower. Block-free is going to be slower than the mutex version. But if you have high contention, then the mutex version obviously is going to be very bad. And then this is where this is going to win. And we're going to see this later in the benchmarks. And then there's another twist. So this is basically what Anthony and Vladislav are doing. And then there's the third implementation, the Folly one, the Facebook one. And they do like an implementation on top of that, an optimization on top of that, which is really cool, which they call ref count batching. And you can look at the code. It's a little bit hard to understand, but David kind of talked me through how it works. So basically, instead of incrementing the global ref count each time you would normally increment it, you kind of increment it kind of in advance by a big number, like bigger than the number of accesses that you expect. And then you don't have to touch it for a while. And then only when you kind of used up the global ref counts that kind of have been handed out, then you kind of have to update it again. So that means that the majority of loads is actually not going to touch the control block at all, and it's going to be just one atomic operation instead of 3, so that we expect that to be faster. That's an implementation. That's like an optimization that they're doing. The trade-off here, though, is that then you don't get a usable use count. Use count is the function that returns the current ref count. So the current ref count doesn't mean anything because they just increment this by a large number up front, right? So it doesn't really, you don't really know what the current ref count is anymore. So that's kind of the trade-off here. All right, great. So, there's an out, yes? So the question is, how would you then know how many pointers there still are? Well, like the internal state knows, but it's kind of spread out over different places. There's no one function that you, as an outside user, can query. Does that make sense? It's more complicated, and I can't say that I 100% understand what's going on there, but we can look at the code together and talk about it. Right. So we have a log-free atomic shared pointer, right? Like obviously this is implementable and implemented, right? This is great, right? Well, not quite. So this is not the whole truth, right? This is a very basic stripped down shared pointer. This is not how std shared pointer actually works. Std shared pointer has a lot more features. First of all, std shared pointer also has support for std weak pointer, which you need to break cycles. So the control block also will have a weak count next to the ref count, right? Then you can have a custom deleter in there. You can have a custom allocator in there. And this is all still okay because it's still all in the control block, and we don't really care about anything in the control block apart from the global ref count, so we're good. But there's one more feature that shared pointer has, which is the shared pointer itself also has a pointer to the object T, right? And it feels that it's maybe redundant, but there's a good reason why there is a pointer in the shared pointer and there's also a pointer in the control block. It's because they don't always point to the same place. One case where this crops up is shared pointer has this thing called the aliasing constructor, which, how many of you are aware of this? Yeah, a few. So it's this weird thing which doesn't occur very often in practice. Basically, you can have a shared pointer which is managing the lifetime of one object, which in this case is this widget here. So we're copying it from the other one. But actually stores a pointer to another object, which is in this case a member of widget. So ideally, the lifetime of the object that it manages and the lifetime of the object that it points to should have the same lifetime, because otherwise you're going to be in trouble. So typically you will point it to a member of the object or maybe a base class of the object. That's the next case. But not necessarily to the same object. And so you would think this is maybe an exotic use case. I've never seen this in practice. Nobody uses this. But there's another use case which is a lot more common, which is this. You have a shared pointer to base, but the actual object is of type derived. Right? And that works, right? So if the shared pointer goes out of scope, it's going to call the destructor of derived, not the destructor of base. Right? So that works. And that is a very important use case, right? If you have, I don't know, a hierarchy of widgets, like GUI widget or something like this is one domain where you might use lots of shared pointers. Then you typically have some kind of GUI widget base class, and then you have shared pointers to that, right? So this actually happens a lot in practice. But because of the way inheritance works, if you have an object and you have a pointer of type derived to that object, and you have a pointer of type base to the same object, in general, they don't contain the same address, because the base class might be There might be multiple base classes, or you don't know what the class layout is, right? So there might be pointers to the same object, but there might be pointers of different type, and they might have different addresses in general, right? So that's why the control block will have a pointer to derived, but the shared pointer will have a pointer to base, and they will be different addresses, and that's why you need to store the other pointer and the shared pointer separately. And now we have a problem, because now we have the pointer to the control block, then we have the pointer to the aliased object, which might be, for example, the base class pointer, and we have the local ref count. So now we have three things. You have two pointers and an index, and we have to modify three things simultaneously, atomically, lock-free. So we need the triple compare and swap, which is not a thing. So now we have a problem. There are solutions to this problem. So there is a particular solution in Anthony's implementation, which you can look up on GitHub, which is really clever. So Anthony has this really clever little lock-free structure, which is basically like a linked list, which can only grow. It can never shrink. You can only do like pushback. That's the only thing you can do. And you can like traverse it. And that's so easy that you can actually really easily implement this lock-free with like multiple readers, just with row pointers. It's like 40 lines of code or something like this. And so he uses this data structure. So what he does is he says, okay, instead of saving a pointer to control block, like the local ref count, and then a pointer to the alias, I'm going to only store an index into this data structure. And so then we can reduce them to half width, right? So we can have one pointer, which is the pointer to the control block, and then the space of the second pointer, like half of that is going to be the local ref count. So that's going to be now on 64 bits, it's now only going to be 32 bits ref count, which is still plenty, right? Still like 4 billion threads, which I don't think you ever have that many. And then the other 32 bits is going to be an index into this data structure, which is going to contain all the alias pointers that somebody has created that are associated with the same control block. You with me? That's really clever. And initially, he kind of pre-allocates inside the shared pointer object like slots for 3 aliases, which should be plenty for, I would say, 99% of the use cases, because who has shared pointers to the same object, and then you have 4 or more different aliases? You know, maybe it happens, but I would say it's not the typical use, maybe. But then if that does happen, then what happens is that you add more aliases to the list, right? You just grow the list. Yeah, and then if you have even more aliases, you add more aliases to the list. And so if you want to like get it out again, you have to kind of traverse the list, so there's a little bit of runtime overhead. But there's a bigger problem. And the bigger problem, who knows what the problem is? Or do you have a question?
So it's a global list?
It's not a global list. It's a list that's associated with this particular control block. So it's like a per control block list. Who sees the problem with this? The problem with this is that allocating slots in the structure, that's a memory allocation. And you have to do that if you have a shared pointer which is aliased, which has an alias pointer, and you want to store this into the atomic shared pointer. This can happen in atomic store, an atomic exchange, and an atomic compare exchange. And this can potentially allocate memory. Allocating memory is not lock-free. Right? You're calling malloc. Malloc, that's not lock-free. So, turns out of all the atomic operations in that implementation, the only one that's actually always lock-free is the load. Because the store can allocate, the exchange can allocate, and the compare exchange can also allocate. Only in a specific case, but hey, it can happen, right? So yes, if you go back to this Twitter thread that I started back in 2019, actually JF noticed this way before I did and said, well, you need, like, don't you need allocations? And Anthony Williams actually says, yes, my implementation needs a lock-free allocator. Otherwise, it's not lock-free. Well, okay. A lock-free allocator means basically you have to allocate all the memory you could possibly need for all these aliases upfront, and then you have like some custom allocator that kind of manages all that pre-allocated memory. But if you run out of that memory, you have a problem. And maybe that's okay if you're, if you have a big system, if you're Google, you have like TC malloc or something going on, you have like a big custom heap that you're managing and you know what's going on. But if you're in an audio plugin, you can't use malloc in there. And also, how would you, okay, even if you had like some kind of like pre-allocated, lock-free allocator, how would you thread this through to like the interface of this like shared pointer? Like it wouldn't really be like such a generic tool anymore, right? It wouldn't be what it is. It would be kind of something else. So it doesn't quite work. So it feels like we have kind of lost here. But here's actually a suggestion that I have to Anthony. I think I know how to fix this. So I'm really curious what Anthony thinks about this. So one thing is that we already discussed by email is, well, you can actually move the allocation from atomic shared pointer store into the shared pointer constructor. So you do the allocation with the lock-free linked list structure at the point where you create the aliased shared pointer, like before you even put it into the atomic thing. So that doesn't have to be lock-free. So you can do the allocation there. So that means like all the atomic operations can be lock-free. So that's great. Unfortunately, that's going to be runtime overhead for every single shared pointer constructor, right? Even if you don't even ever use the atomic shared pointer, just the normal shared pointer, you're going to pay for this overhead. But again, there is a solution here. So there's one thing we can do, which is we can observe, and this is something that I came up with like literally a couple of weeks ago. So I'm really curious to like put this in practice. You can use the fact that if you have an aliased pointer, you typically will point either into a base class of the object or you will point to a member of the object. But these are like all the use cases that I have seen anywhere. So you will point to a location which is within the other object, right? It's not going to be like some kind of random other unrelated memory location. So you're going to point to some location within that object. So what you can do is you can actually compute the difference between those two addresses, right? You can take the address to like of the pointer to the object in the control block. You can take the address of the aliased pointer, which is going to be somewhere within that object, and you can diff them, and you can get the difference. And that difference is probably going to be a number that's going to fit into half a word. So if you have 64-bit pointers, probably the difference is going to be 32-bit. And you can store that instead of the index into this structure, and you don't need the structure anymore, right? So this is basically the idea. So if the difference fits into 32 bytes, which it always will be if your object is smaller than 4 gigs, basically, you just store that difference directly, and then you can get the aliased pointer out of that afterwards. And only if the difference is bigger than 4 gig, you can still use like the Anthony's linked list structure, but you allocate in the shared pointer constructor. So you will pay this overhead in the shared point constructor, but only in this like really, really exotic like edge case where you have an aliased pointer that's more than 4 gigabytes away from like the object pointer, which I don't think really is going to happen in practice. Yeah, even in that case, yes, you have this like overhead with like additional allocation in the shared pointer, but in all cases, all the atomic operations are going to be lock-free. So that's great, right? So we solved the problem. Do we now have a lock-free atomic shared pointer? Well, we are relying on double with compare and swap. And that's another area where I found it really, really difficult to get a straightforward answer to the question, do we have double with compare and swap? And there seems to be lots of different opinions flying around, and I had to dig a bit deeper to figure out what the state of affairs actually is, because different people were telling me different things. Some people were saying, oh yeah, every modern CPU has that, no problem. Other people were saying, oh, no, don't use this is like non-portable. And actually, the reason why Vladislav decided to re-implement the whole thing, because he said, Anthony is using double with compare and swap. You can't do that, this is not portable. So he went off and like did his own implementation, basically because of that. So I was like, oh, okay, something I still don't quite understand. What's the truth here? So I did some digging, and actually last week I wrote like a whole blog post on my blog, timur.audio, just about that, just about double with compare and swap. So you can get all the gory details there with like Godbolt links and everything. I'm going to just like summarize it here very quickly. Do we have double width compare and swap operations on modern CPUs? Yes, we do. On Intel 32-bit, this is available. There's an instruction called compx8b. On 64-bit Intel, which is obviously a very important platform, this instruction, the 16-byte version of that instruction is exactly what we need, is available on all Intel-compatible CPUs since at least 2008. There are some early AMD chips that don't have that instruction, which date from 2008 or earlier. But for example, Windows doesn't even run on those chips, right? Windows actually requires double width compare and swap since Windows 8.1, 64-bit, right? And macOS also doesn't run. Like some Linux versions might run on those old chips. But like, if you have chips that are 2008 or older, you definitely have double width compare and swap support in there in the hardware, guaranteed. And on ARM, it's a bit different. You actually have a different way this is implemented in hardware. You have something that's called a load lock store conditional. It's like a little bit of a different mechanism. There's actually a difference there between compare exchange weak and compare exchange strong. There is no such difference in Intel, but there is on ARM because it's implemented differently. But on every modern ARM chip that I could find, like you have the right instructions. It's supported, both 32-bit and 64-bit. So we do have our CPUs support this stuff. There's no problem there. Other people have said, yeah, but it's too slow, right? We don't want to use double width CAS because it's too slow. I was like, well, how slow is it? So do we have a performance problem there? Again, I couldn't find anything conclusive, so I went on and measured it myself. I found that pretty much on Intel 64-bit, double width compare and swap is about twice as slow as normal compare and swap, which makes sense because it's doing double the work. On ARM, the overhead is even lower than that. So it's not 5 times as slow, it's not 10 times as slow. I don't think we have a super extreme problem here with performance. I actually tested this like with the oldest chip I had at hand at home was like a Mac Mini from 2014, and also on that somewhat older machine, double width compare and swap was also just twice as slow and not 5 times as slow or 10 times as slow. So I don't think, I mean, I haven't obviously tested a lot of different hardware, but like as far as I'm aware, we don't really have a massive performance problem here. The much more interesting question is, does the atomic support double width compare and swap? In other words, if we have this stuff here, this is basically how it looks, how Anthony's implementation looks, right? You have like this struct, and you have pointer to control block, and then you have half a pointer with the local ref count and another half with like the alias index. And then you also have to align this with like double width, so that like the double width variable doesn't straddle two cache lines. So that's what the aligner is for. And then basically the question is, okay, we do all of this, we know our hardware supports this, but is the static assert going to fail or is it going to pass? What do you think? Is it going to pass? Who thinks that? Yes. Sorry? Sorry, I don't hear you. Can you speak up, please? The decal type value. Oh, again, that should be decal type atomic C-putter. Sorry, I need to fix this. So it's like the atomic counted pointer, and it's the decal type of that. So it's just atomic counted pointer. Sorry, I have a mistake here again. I have like 2 different variable names here. So value should be atomic C-putter. Apologies. I will fix that for the next version of this talk. Who thinks this static assert is going to fail? Okay. Who thinks it depends? Okay. So this is me in 2022. Our CPU supports double width compare and swap. Surely still atomic does as well, right? So I went on, and actually this is all in a blog post. Actually did this exercise of testing it on all compilers on Godbolt that I could think of. And basically this is the result. Basically just whether this static assert fails or not. And yeah, I tried this on 32-bit, 64-bit Intel ARM, and on like all 3 major compilers, plus also Apple, which I tried on my own, like multiple MacBooks that I had at home. And this is the result. And basically, yeah, there's like a whole long blog post about like what's going on there, but I'm just going to give you like the ultra short version, which is on 64-bit Intel and on ARM, basically you don't have double width compare and swap support across compilers because of ABI. That's basically the short version. So it's another one of those really sad instances where implementers choose ABI stability over performance, which I think is really, really sad. But that's the way it is, and there's not much I can do about this. So what are the possible solutions? Well, one solution is implement our own state atomic, which on macOS it's trivial because it just works, right? They have their own Apple clang where like, you know, they kind of basically doing the right thing. On Windows, it's still fairly easy because State Atomic doesn't support it, but this is actually one of those typical Microsoft compiler things. So State Atomic doesn't support double compare and swap because they can't change the ABI of State Atomic. But we have a new thing in C++20 called State Atomic Ref, which does support it because it's a new thing, so there's no ABI to break, so we can give it the latest features. And also there is actually a Windows API function called interlocked compare exchange 16 underscore something, which is basically also doing this thing. So you can basically wrap that and like you can easily like put together your own kind of atomic that does the right thing on Windows. On Linux, however, in order to do this, basically I would have to re-implement libatomic or like large parts of libatomic, and I don't know how to do that. This sounds like quite a lot of work. Maybe one day I will learn how to do these things, or maybe somebody knows a library solution that already exists, but I don't know one, so that's very sad. So it's not really a practical solution, unfortunately. And the only other solution that I can think of is don't use double width compare and swap. But how are we going to do everything we talked about without double width compare and swap if we only have compare and swap or any atomic operations on one pointer width? Turns out, well, you can do it. It's a technique called packed pointers, which is used actually by both of the other free and open source implementations, both Vladislav and also Folly. They both used packed pointer, and I'm aware of at least one closed source implementation of another company that has implemented it as well, which I don't have access to that code. I just heard that it exists, and they also use pointer packing. And it only works on 64-bit. And basically the idea is that 64-bit Intel actually doesn't use the full 64-bit address space. It only uses 48 bits. And actually even less than that, because you have like 3 bits of alignment, which you can always use. Because if you allocate memory, it's always going to be aligned to at least SIP-max align T, which is at least 8. Sometimes it's even 16, depends on the platform. Anyway, so you can use those bytes for like bits for like flags or something. But more importantly, you have 16 bits at the front, which are not used for anything. And so you can just put values in there. So this is the current situation on Intel 64-bit. So they basically have this 48-bit address space, which can address 256 terabytes of memory, which should be plenty for everybody. They did implement 5-level paging, which raises this to 57 bits, I think. But and there is, I think, hardware already that does that, and there's even, I think, a Linux kernel that supports that. But this is not like something that you would see in consumer hardware today, and also like on this like hardware where you do have this. As far as I know, user space applications will still see the 44 8-bit address space, because surprise, Hiram's law, there's actually a lot of software out there that depends on these 16 bits not being used, right? So we are good for at least a while on this. Probably not forever, but for the time being, we're okay with this on 64-bit Intel. And turns out on 64-bit ARM, it's actually a very similar story. They also have either a 39-bit or a 48-bit address space that they're currently using. And again, they have recently extended this to 52-bit address space, but again they say, but this is never going to be used, or this is not currently used by like user space applications. Like there's a guarantee that these like 16 bits are not going to be used. So what we can do, and this is what both Folly and Vladislav are doing, we can now have one atomic variable, which is 64 bits big, which is this atomic U-interpreter T value. And now the static assert that it's lock-free, it's definitely going to be true, right, on any reasonable platform. And then we basically pack, like, we have 16 bits of ref count, which is still plenty. And then we have, which is like 65,000 threads or something. And then we have, like, the rest is the address, right? And then every time we get the pointer or the count, the ref count, local ref count out, we need to, like, do this offset and mask. And if we set them, we have to do them in reverse. But you can probably imagine what that would look like. There's one worry here. Maybe there's actually this line. There's like a hidden reinterpret cast here, right? Because we cast the U-interpreter T to a T star. So it's like an implicit reinterpret cast that's going on in there. It's like casts in C++ are nice. But actually, it turns out it's OK, because the address that we're returning there actually points to an object of type T that actually lives at that exact address in memory. So this is actually the one use case where reinterpret cast is actually OK to use and does not introduce undefined behavior. So we're actually good. And with this, we arrive at this implementation where we have, again, our shared pointer on the left and the control block on the right, but the shared pointer now just has this atomic packed pointer value, which contains both the control block pointer and the local ref count in one 64-bit atomic variable. And now we can do the whole algorithm again, and everything works. Everything's fine, and we have our lock-free atomic shared pointer. Except we have to deal with the alias pointer case, right? And now we definitely don't have any space to put this anywhere, so there's no tricks you can use here. So I looked at what the implementations are doing. Vladislav is actually just not handling that case, so if you create like a shared pointer to base and give it a pointer to derived, it just crashes. Folly does handle it in a way that they actually then, they have a bit, I think they use one of the alignment bits, whether it's an alias or not, like using as a flag, whether it's an alias or not. And if it is an alias, then instead of having a pointer to the control block, actually that arrow at the top should then disappear. I'm going to fix that as well. So there is no arrow from value to object pointer there. So they're wrapping the control block into another wrapper, which they're just using another shared pointer basically for this. And so if you have an alias, you don't have this pointer to control block, but you have to go through this indirection. You have to have a pointer to the other structure, which is like basically another control block, which then has the pointer to the alias and the actual control block. So you have this like extra level of indirection. This is what Folly is doing, and it works, except, of course, allocating this alias wrapper is another memory allocation. So in the Folly implementation, also atomic store, atomic exchange, and atomic compare exchange are not actually lock-free, which is very sad. There's one way around this, which I suggested before. I'm just going to repeat it. We can move that allocation from the atomic shared pointer to the shared pointer constructor, and that's going to make the atomic functions lock-free again. Unfortunately, this time, we will have this overhead for every alias shared pointer, and there is no way we can get rid of it the way we did for the double with compare and swap case, because there's just not enough space to store this like diff pointer or anything like this. We only have 64 bits to work with. So this time, if you want to have lock-free atomic operations, we do need to pay this overhead, basically. Whenever you create a shared pointer, and you give it an alias pointer, it will create this extra memory allocation. But at least the atomic operations are going to be lock-free, right? So it's kind of a compromise, but I think it works. Because probably you're going to have, in this scenario, a shared pointer that you will use specifically to be used with atomic shared pointer. So we are nearing the end of the talk. Here I put together this like little overview over the 3 implementations that I have access to, which are free and open source, which are on GitHub. And this is what it currently looks like, right? None of them are really portable because they either depend on double with compare and swap, or they depend on bit packing, or the most hilarious one is Folly. So for some reason, Folly had this internal requirement that they I should say, Anthony Williams and Vladislav, they both have their own shared pointer as well as their own atomic shared pointer, so that the shared pointer works well with the atomic shared pointer. So for Anthony, actually, it's important because in his version of the algorithm, the control block has to be aware of the split ref count. Folly, however, wanted to use the normal std shared pointer. So what they're doing is they just built the whole thing on top of libstd C++ std shared pointer, which is like the GCC shared pointer. So their version is only ever going to compile with GCC. They say they accept pull requests for other standard libraries. What they're basically doing is they're like building this on top of GCC std shared pointer, and then they have this like hack where you can get access to a private variable if you do the explicit template instantiation. I don't know if some of you have seen this hack. So that's what they're doing basically to reach into the guts of GCC std shared pointer, get to the ref count, and mess around with the ref count. And so this is unfortunately only working on GCC. So it's not portable. None of them have lock-free aliased pointers, as we discussed. The only one that's more or less standard conforming, so more or less implements like everything that the standard says a shared pointer should have, is Anthony Williams. But Folly is also the only one which is, as far as I know, used in production. So the Anthony Williams version that's public on GitHub is a proof of concept. It does have bugs. I did find multiple bugs that are reported to Anthony. Vladislav's version is very incomplete. It doesn't have an exchange. It only has a compare exchange. It doesn't support aliasing. There's like other problems with it. So maybe the commercial version of Anthony Williams's atomic shared pointer is actually kind of more tested, but I don't know it because I've never seen it. So yeah, this is kind of where we are currently if you want to go free and open source. Benchmarks. So I looked at those and I actually measured them. And how did I set up because I wanted to know how they perform. And how did I set up these benchmarks? And by the way, I don't think this is the best way to do this. And if anybody has an idea how to benchmark this in a better way, I would really appreciate input. Basically, what I did here is I have an atomic shared pointer at the beginning, like a global one. This is the aperture. And then I have some number of threads which are just hammering that atomic shared pointer. Like there's like just a cast loop, and every thread just tries to assign its value to it, right? In an infinite loop. So you have like some number of threads which are just like hammering at that atomic shared pointer all the time. And then we have this one thread where we're actually measuring, and then we are seeing like how long does it take to do one load, one store, one compare exchange, or like one cast loop until it succeeds. And we vary the number of other threads. And then we plot that. And if you look at the load, it looks like this. So one of the compilers where I can actually compare implementations is AppleClang, because that's where W with compare and swap works. And that's where Vladislav's implementation also works. And so the third one, so the black one is actually the standard library, the freestanding functions. I wrote like a little wrapper around it, so it's kind of the same thing. But like you're basically testing the freestanding functions, which have a mutex in them, against Anthony's implementation and Vladislav's implementation. And what we're seeing is kind of what we would expect. So the kind of blob in the middle is the median, and then the bars are like the lowest value that I measured and the highest value that I measured out of a bunch of runs, right? So you see that the lowest value and even the median value is lower for the mutex version, actually. So on average, the mutex version is faster. Yes, because acquiring a mutex is a lot faster than doing all this cast loop stuff, right? But if you look at the top bar, like what the worst, like slowest instance of executing that particular load was, then we see that the mutex actually performs really badly, because every once in a while we get really unlucky and we like wait a lot on that mutex. We wait for a very long time. And you can wait hundreds of microseconds for it, which, for example, in an audio plugin would be completely unacceptable. And so that's kind of the black bar that goes all the way up. And then we see for the lock-free implementations, that top bar is a lot lower, right? So they are, on average they're slower, but the worst case is a lot better. And when we do low latency programming, real-time programming, we really care about the worst case because we're on a deadline, right? So that's why we should use the atomic lock-free versions. And you also here see that the Vladislav's implementation is about a factor of 2 to 3 faster than Anthony's. So there's 2 reasons for that. One is it doesn't use double with compare and swap. It just uses one with compare and swap, which is faster. And the other reason is that if you cram everything into like one 64 bit variable, then you can get rid of some of the cast loops because, for example, increasing or decreasing the local ref count without modifying the control block is just an increment or just a decrement instead of a cast loop, because you're not dealing with two variables, you're only dealing with one variable. So like a little optimization happens there if you use packed pointers. So this is why it's faster. If you look at store, compare, exchange, and a compare, exchange loop, it looks slightly different. It turns out that Vladislav has a particularly unfortunate and slow store implementation, where basically his store just calls like atomic shared pointer compare exchange in a loop, which is not an efficient way of doing this. So Anthony has like a better implementation here. So here, Anthony's version outperforms Vladislav's, which is where the store is particularly slow. And then if you look at compare exchange, it's kind of similar to load, but the compare exchange loop, again, is bad. Because if you do a compare exchange loop, a cast loop, with an atomic shared pointer, you basically have a nested cast loop, right? So you have a cast loop, and then each run has this whole machinery with like another cast loop inside. So you have like a nested cast loop. That's going to potentially take a while if you have a lot of threads, right? So you should avoid atomic log-free shared pointer compare and swap loops in log-free code because they do not perform very well. And then the other compiler I could check is GCC, because on GCC, unfortunately, Anthony's implementation doesn't work on GCC because you don't get double bit compare and swap. But I get the Folly implementation on GCC, so I can compare the standard library version with the mutexes with Folly and Vladislav. And here we see kind of a bit of a similar picture, except this is Linux. This is also a different machine. So there's like a different thread scheduler, different mutex. So there, the mutex version performs better than on the Mac in comparison. But like, still the load looks very similar to like the previous slide. But here, interestingly, we see that even though Folly uses the batched ref count, it doesn't really outperform Vladislav, which doesn't use that. So that I was a bit surprised by that. I was expecting the Folly version to perform a lot better than Vladislav here because it uses the batched ref count optimization. So I'm not entirely sure whether maybe that benchmark that I used wasn't exactly the best way of measuring this. So maybe there is another way I need to benchmark this. So I haven't quite figured this out yet. And then basically, again, Vladislav has an inefficient store. Compare exchange is fine, and the compare exchange loop is actually really quite slow again on all three implementations. Okay, we're almost at the end. Takeaways. Is a log-free implementation of std atomic shared pointer possible? And I think you should know the answer right now. Yes, it is, if you either have double with compare and swap, or you have unused pointer bits that you can use. If you don't have double with compare and swap, there's a few trade-offs. So depending on how many free bits you have, that's going to determine how many threads you can have, because that puts a limit on your local ref count. And then if you want to support the alias case, which you really have to do because it's quite common, you will pay this overhead with every shared pointer constructor that creates an alias pointer. And then you have other conformance versus performance trade-offs, right? So you can do this like batched ref count batching, but then you lose the ability to call use count. And, there are other trade-offs like this. Like if you don't want to have this feature, which is specified in the standard, then you can do this optimization. So there's like a scale of like different trade-offs. But like in principle, yes, it's implementable. The real question, of course, is a log-free implementation of std atomic shared pointer implementable in the standard library without an ABI break? Because that is the question that we need to answer if you want to know if you can ever have this actually in std. And, well, back to that Twitter conversation. Anthony says, well, the shared pointer block needs to be aware of the split ref count because of the way my algorithm works. So I can't use std shared pointer. I need to implement my own shared pointer. Turns out that's not a requirement in general. It's just in the particular way Anthony has written his version. Neither Vladislav nor Folly have such a requirement. And in fact, Folly is written on top of std shared pointer, the one from the GCC standard library. So in general, yes, it is possible to implement this without an ABI break on std shared pointer. So, maybe I don't know if I'm being super optimistic that perhaps maybe the Clang people might come up with a lock-free version, although I'm not getting my hopes up very much. But I would love to hear from them. So as I said, this is an ongoing project. Actually, I'm working on my own implementation because, yeah, I don't think this, like, I'm just going to write my own implementation. What can possibly go wrong? So I'm now also one of those people, like Vladislav. But basically, I want to learn from this, right? And maybe it's going to be useful. So one thing I want to do is I want to figure out how to benchmark this better because I don't think I got that quite right. And then, yeah, my own implementation, which I'm working on, which is currently not finished yet and not in a presentable state. I want to make it more portable by being able to switch between double compare and swap or pointer packing. I want to make it actually lock-free, which none of the other implementations are, by moving this allocation out of the atomic store, the one that we need for the alias pointer. And then I need to experiment further with refcon batching. I'm not really seeing a benefit in the benchmarks, but then it sounds like it's a really clever idea. I just need to figure out how to prove that it is, or I don't know. And then I want to come up with an implementation that's complete enough that I can actually put it on GitHub, and then you all can look at it and tell me what I did wrong, or maybe whether it's usable or whether it's correct or not. That would be really, really cool. I'm not quite there yet. And a potential goal would be to actually implement, support double with compare and swap on more platforms by actually kind of implementing my own atomic that actually forces double with compare and swap everywhere, which is kind of what I want. But it sounds like a pretty daunting task, especially on Linux, so I might never get to it. And I would really love to know, maybe somebody has already done it. Last slide, we saw already this, right? Like these are kind of the matrix of like existing open source implementations. So this is where I want to be, right? But this is work in progress. I'm not there yet, but this is where I want to be. I want it to be more portable. I want it to be actually lock-free. I want it to actually conform to the standard, like implement the full interface of atomic shared pointer as specified in the standard. And hopefully one day, somebody will use it for something useful, or maybe not. But yeah, as I said, this is work in progress, but hopefully I will make progress on that in the future, and I would love to hear your feedback on this. This is all I have for today. Thank you very much. The question was, I'm just going to repeat the question, how to verify that the code is correct. Yeah. And I have actually posted this question on Twitter a few months ago, like, how do you verify that your lock-free code is correct? Because I had no idea. Well, it turns out, like, if you really want to be correct, then you need to like formally prove it, but I have not found a framework that would allow me to do that for these types of algorithms. So then basically the answer that I could find was write a bunch of tests with lots of threads and run it through thread sanitizer and all other kinds of sanitizers that you can find, and run that on CI and like hope that they catch all the possible race conditions.